Have to let me know when you think it's all said and done.
I have a question.
I started the lecture. Does it have to do with the lecture?
Yeah.
All right, what's up?
Actually, never mind.
All right, we can leave the end of the lecture open for whatever questions. I just want to get through today's material at least. All right, next section, we're starting on probabilities. Ton of fun.
Yeah.
Probabilities, one of the funnest chapters and one that we're going to spend the most time on. One of the ones we're going to spend the most time on. I think it's the biggest, but I'm not positive. Now, hopefully you've all come across probabilities before, and so you can answer some simple questions, like if I flip a fair coin, what are the odds it comes up heads?
50.
50%. If I flip a fair coin twice, what are the odds I get heads twice?
25.
25%. Is everyone okay with how we got that? If I flip a coin, and what are the odds it comes up heads the first time? 50%. And then if I flip it twice, what are the odds I get heads twice in a row?
50. 25 twice correct. But 50 for the second accurate.
1/2 times 1/2. 25. Look. I flip a coin once. I can either get heads or I can get tails. Those are both equally likely, so 50-50. I flip a coin 4 times, what are all the possible outcomes? Or sorry, flip a coin twice, what are all the possible outcomes? I could have gotten heads, heads, tails, heads, heads, tails, tails, tails. Those are all the possible outcomes. What are the odds that I got heads twice in a row? 25%, 1 in 4.
Got it.
All right, well if I were to flip a coin 3 times, what are the odds I get heads 3 times in a row?
33.3.
No, it's me.
It's going to be 12.
What?
12 and a half. Is that the right number?
It's going to be a probability, it has to be less than 1. Can't be more than 100% chance of something happening.
12.5%. Well, there's going to be
Oh, 12.5%.
Yeah.
Yes,
1/8.
or 1/8. How are we getting that?
Because you just multiplied.
1/8.
There's 1/2 chance I got heads the first time, times 1/2 chance I got heads a second time, times 1/2 chance I got heads a third time.
So 50.
1/2 times 1/2 times 1/2, or an 8. Or you could have written down all the possible combinations. If I were to write all the possible strings I can make using the letters H and T that have a length of 3, how many strings can I make? If I'm making a string of H's and T's here,
2 times.
so like HHT or TTH, how many can I possibly make?
6.
No. How many options do I have for what comes here?
2 cubes.
2. Heads or tails. How many options do I have for what goes here?
2.
2. Heads or tails. How many options do I have for what goes here?
2.
Heads or tails. So 2 times 2 times 2 is
2 cubes.
8.
4. 8.
8. So there's 8 possible ways I can flip a coin 3 times. One of those 8 ways is 3 heads. So 1 in 8 ways I can get heads 3 times.
Yes.
Let's make sure you're getting this. Let's extend this to I flip a coin 4 times now.
2 to 4.
How many possible outcomes are there? 16. Right? We could have gotten heads, 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 tails, tails, heads, heads, tails, heads, blah, 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 and I could list them all up. There's 16 of them, right?
Okay.
2 options for your first flip, 2 options for the second, 2 options for the third, 2 options for the fourth, 2 times 2 times 2 times 2, 16. What are the odds that I got heads 4 times in a row?
1/16.
1 in 16. One of those 16 outcomes was heads, 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 heads. Right?
6.25%.
So do we use percents or fractions?
Fractions. Fractions are preferred. You can use percents if you want. Okay, so I have a fair coin. Everyone know what I mean by a fair coin?
It's not rigged.
It's not a rigged coin. It's a fair coin. It's not loaded somehow to come up heads, more, and tails.
Is that even possible?
Huh?
Is that even possible?
Close enough to possible. A coin is very, very, very close to fair. Anyway, so we have a fair coin. What are the odds that we flip heads, heads?
25%.
25%. We get here? Okay. If I flip a coin twice, what's more likely? I get 2 heads, or I get a heads and a tails.
They're the same likely.
Or are they the same likely? Is it a trick question?
Heads and tails.
Is it more likely that I get one of each, or that I get 2 heads.
Oh, one of each, yeah.
Yeah.
I thought it was meaning in order.
No.
Okay. Then it's one
No,
of each. Or
heads and
tails,
tails
black.
is 50%. 2 heads is 25%.
Good. So let's write them all out. We can get heads, heads. We can get heads, tails. We can get tails, heads. We can get tails, tails. How many ways can we get one of each? 2.
50%.
How many ways can we get 2 heads? 1. So 1 and 4 gives us 2 heads, whereas 50% of the time we get 1 of each. Make sense? Now, what's more likely? That I get heads, heads, or that I get heads, tails?
They're the same likely.
Those are the same likely.
Yeah.
Understand the difference between getting heads, tails, and getting 1 of each.
Order.
Yeah, word matters. All right. Great question. Maybe, hopefully, some of you have already come across this question before, but good to keep in mind when we talk about probabilities. Jack and Jill. I tell you, Jack and Jill have 2 kids. One of them is a boy. What's the odds that their other child is also a boy? 50%, right? 1/2. Because there's 50% chance of having a boy, 50% chance of having a girl. Jack and Jill have 2 kids. One of them is a boy. What's the odds that their other child is also a boy?
And whose family?
50%, right? No.
Wait.
The answer's not 50%. See if someone can get it before I write it.
It's 25%.
No.
No. Yeah.
That the other one is a boy?
Jack and Jill have 2 kids. One of their kids is a boy.
Oh.
What's the odds that their other child is also a boy?
It's like 75%.
No.
It's higher than 50.
No.
It's literally a
25%.
quarter. 25%.
All right, let's think this through.
A third.
You can do the one
It's a
before.
third.
Yeah. No, duh.
Jack and Jill have 2 kids. What are all the possibilities? They had a girl, then a girl. They had a girl, then a boy. They had a boy, then a girl. They had a boy, then a boy. These are all the possibilities, right?
Yeah.
I told you one of their kids is a boy,
Cross out
so can't be that.
that's weird.
What is the odds
Oh.
that their other child is also a boy?
1/3.
All 3 of these outcomes are equally likely. Only one of those 3 includes 2 boys, so there's only a 1/3 chance that their other child is also a boy.
So if you said girl, it would be 2 things.
Well, girl, boy, girl, the same thing.
Right. If I said no,
If you said
Order doesn't really matter in this, unless you want to cross out the girl, boy.
Having
Because
a
boy
child.
can't.
having a girl than a boy is definitely different than having a boy than a girl.
it's the thing with
You said that they already had a boy, though.
Flipping,
No, I said one of their kids is a boy.
Chandler, flipping tails and heads is different.
They have 2 kids.
It would be different.
You know one of them is a boy. You don't know if the older kid is a boy or the younger kid is a boy. All you know is one of the kids is a boy.
But what's the chance that the other kid is also?
It's like I flip a coin twice, or I have 2 coins. I flip, and I cover them up. I tell you one of the coins is a heads. What is the odds that the other coin is also a heads?
I guess it's 1/3.
It's only 1/3.
Order in which you flip it matters. And which one you flip first.
There's 4 possible outcomes.
Yeah.
Heads, 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 tails, tails, heads, tails, tails. Getting heads on the first coin and tails on the second coin is a different outcome than tails on the first coin, heads on the second
I
coin.
just didn't have a problem that order matters of which one came first.
Right, matters for the same reason.
Chandler, we
Make
didn't-
sense?
we didn't need to make.
No, it's all good. Make the mistake and think it through, make sure it makes sense to your intuition. That's the reason I introduced these early on. Is because I know that you're going to get stuck on these and you're going to answer them wrong because our intuition is awful when it comes to probabilities. Nobody magically just gets probabilities. Probabilities are something you have to study to understand. So after this, we're going to get to the definition of something called a sample space. And you are going to feel like it is way overkill for the problems that we're talking about. I'm going to make you go through full-fledged creating sample spaces for all the probabilities that we talk about. And it's going to be real easy for you to just already know the answer to the problem in your head without going through all the work of creating a sample space. We'll get to what that is here in a second. My point is, don't skip the sample space step. You're going to feel like skip straight to the answer because it's going to be easy questions like, what's the odds of flipping heads twice to begin with? But eventually the questions are going to get hard enough that your intuition is no longer just going to be able to give you the answer. And to get the answer, you're going to have to go back to the mathematical model and actually make sure you understand it. So that was dipping your toes into probabilities, hopefully making you understand they're not intuitive. It's going to feel weird the first time you come across them. That's universally the case. All right, so starting with this section, teeny section in the book, you can read it real quick. One of the small sections in there. But we'll do more of a deep dive than the after that. And it is on sample spaces. What is a sample space? A sample space is an ordered pair S comma P, where S is a non-empty set and P is a function that maps from S to the real numbers. Such that P of S, the right-hand element for any particular S is always greater than or equal to 0 for all S, and the sum of all the probabilities is 1. Okay, that seems like a mouthful, that seems complex. Seems like there's a lot going on there. Let's make sure we understand it. So S here is going to be the set of all outcomes. Let's go back to our Jack and Jill problem. What were all the possible outcomes if you know that Jack and Jill have 2 kids? Yeah, what were they?
Boy, boy.
They could do boy, boy,
Boy, girl.
boy, girl,
Girl.
girl, boy,
Girl, girl.
girl, girl. Sorry, I'm going to use it. Getting a little sloppy. Girl, girl. The set of all possible outcomes, that's what S always represents. The set of all possible outcomes. That's intuitively how you think about S. It's a set of all possible outcomes. It's just a non-empty set. Non-empty because we have to be talking about at least one possible outcome. But then some set. Now what is P? P is our probability function. P is our probability function. So up here, our probability function, what was the probability of them having boy, boy?
25%.
25% or 1/4, right? What was their probability of boy, girl? 1/4. What was their probability of girl, boy? Girl, boy was 1/4. And then finally, their probability of girl, girl was 1/4. Now, how do I know that doesn't make sense for the probability of their girl, girl to actually be 1/2?
So it has to equal.
Because it has to equal 1. I can't have over 100% chance of one of the outcomes happening. I can't say, when I flip a coin, there's a 50% chance it will come up heads, and a 79% chance it will come up tails. If there's a 50% chance for heads, there can only be a 50% chance for tails. Let's say I created a bias coin, a weighted coin, so it comes up heads 60% of the time. How often does it come up tails?
40%.
40% of the time. Because the probability has to add up to 1 when you include all the outcomes. That's what this condition is saying. The sum of all the probabilities has to equal 1.
Good.
So this has to be 1/4. Right? So now let's read this definition again, and hopefully you get it. A sample space is an ordered pair, S and P, where S is a non-empty set, we typically call that the set of outcomes, and P is a function, we call it a probability function, that maps each of your outcomes to some real number, their probability. We require that the probability of each outcome is greater than or equal to 0. Doesn't make sense to say there's a negative 17% chance of that happening. And we require that the sum of all the probabilities sums up to 1.
Oh, okay. Yeah.
That's what it's saying. It's a big definition, but pretty intuitive when you just think about how you would set it up yourself. Good? Great. So, I redid this. Example. Sample space for this. We did the exact same thing. Notice the sample space is S and P together in an ordered pair. When I ask you to write the sample space, that is not asking you to write the set of outcomes. That's a common mistake students make. This is a set of outcomes. This is a probability function. Writing them together in an ordered pair is what we mean by the sample space.
How do you do that?
BB.
Exactly like I have written there. Here's what S equals, here's what P equals, here's the sample space.
Oh, sample space.
The sample space is the ordered pair of the two. This is a sample space. This is not a sample space. This is a set of outcomes. This is not a sample space. This is a probability function.
So how would you write a sample space? Like
right there. You could have, if you wanted, instead of writing S, you could have taken that set and written it there, comma, taken a probability function and written it there, and put those in order if you want.
So,
You can do it like that, or you can label the variables and say, here's my sample space. S is that,
okay,
P is
that's
that.
what you mean.
Yeah. Just making sure you understand what the sample space is.
Can't you just write P, because P has all the S in it already?
No, we don't do that. It's common when you're talking about a set, when you're talking about some mathematical abstraction, like in algebra or a group or whatever. So in algebra, you're talking about the real numbers. So you're talking about the real numbers together with two operations, a plus and a times. This is talking about a set S together with some function, a probability function. So a set together with some structure on the set is a very common thing that we do in math over and over again. And it's nice to have the set separated from the structure on the set. Because technically, couldn't you just look at the plus function and look at all its domain to figure out what the real numbers are? Well, yeah. But we want to be able to say that plus is a function from the R cross R to R. And so we want to use R in this definition, the same way we want to use S here. So, no, we keep it separate. Don't just write down the probability function, write down both. Okay, so another example. Let's talk about rolling a fair die, six-sided die. I've got a six-sided die, I'm going to roll the six-sided die. What are all the possible outcomes?
1, 2, 3, 4, 6.
Right, we can get 1, 2, 3, 4, 5, and 6. So here's our set of all possible outcomes. And we'll assume that it was a fair die, since that's what was given to us. And so the probability of 1, 6, or of 1 is 1, 6, of 2 is 1, 6, etc. You with me?
Yeah.
Perfectly valid way to do our probability space. Notice here that 1 went 1, 6, 2 went 1, 6, 3 went 1, 6, 4 went 1, 6, 5 went 1, 6, 6 went 1, 6. Everything in S just mapped to 1, 6. We have a shorthand for that. We say P of little s is equal to 1, 6 for all little s and big S. So when your probability function always spits out the same thing, we just write it like this. Make sense? Okay, so that's just notation, shorthand, so we don't have to write out functions like that where they all go to the same thing. Now, there is no such thing as the right sample space for some physical phenomenon. We're talking about the physical phenomenon of rolling a dice. And I said, what is the sample space for that physical phenomenon? There isn't the sample space for some phenomena. There's some that you might think are more useful, there's some that you might think are less useful. But there isn't the right sample space. So let's look at another sample space for rolling a die. I decide to call S the set of these things. And I decide to call my probability function, this thing goes to 1/2, this thing goes to a tenth, a tenth, a tenth, a tenth, a tenth. Is this a sample space?
Yeah.
Yes, it's a sample space. Is it a sample space for rolling a fair die?
Not necessarily.
Not a useful one, but yes, it is still a sample space. So this is a perfectly valid sample space. It's not a very useful one when we're talking about rolling a fair die.
But then it wouldn't be a fair die.
You're trying to impose some mathematical structure on the real world. We have a fair die. Here's a sample space I come up with. It's not a very useful one, but it's still a sample space. Does it meet the definition?
Yeah.
So it's still a sample space. So you don't need to call a sample space right or wrong. You need to call it useful or not useful.
So on homework, is it just going to be like, what's the most useful?
It'll be very clear what you're supposed to do. So let's give another example. You're out in the real world, stumbling around, and you come across this thing. Sorry, this is supposed to look like a spinner. I couldn't draw on the red chalk very well. That's supposed to be like a spinner, and you can flip the spinner and it spins around. You with me?
Yeah.
And I put the 1, the 4, the 3, and the 2 out here because when I tried to draw that, I realized I can't draw on the colored chalk. But pretend that 2 is what we call that. 3's there, 4's there, 1's there. All right, now we want to come up with a sample space for spinning the spinner. How might we do it?
1, 2, 3, 4.
So I would have S goes to
1, 2, 3, 4.
1, 2, 3, 4. That's one way we could do it. Where P is
1 pairs to 1
1/2.
half.
1 pairs to 1/2. Okay. 2 pairs to 1/4.
3 and 4 pairs to 1/8.
3 pairs to 1/8. 4 pairs to 1/8. So here's one sample space that you might come up with. What's another one we might have done?
I have a question.
Go ahead.
Can you change the order of S?
Yeah, it's a set. Order doesn't matter.
Okay.
This is equal to the set 4, 2, 1, 3.
So what if you did like, if you changed the order, then would B become like that same changed order? So it would
This,
be
I could
4
change the order of this. This is still a set. This is a set of ordered pairs. The order that I write the ordered pairs in does not matter. We write it this way just as convention. Okay, so what's another way that we could have done this?
P of S goes to 1/4.
I could have had S is equal to,
All
Red.
lines go to 1/4.
right, I could have had something like red, red, blue,
orange, yellow.
orange, yellow. And then my probability function could have been something
R.
like R goes to
1/2.
1/2, B goes to
1/4.
1/4, O goes to
1/8.
1/8. Now it doesn't have to be 1/8. Maybe I pull out my measuring stick and I measure this a little bit better and I say, he's getting a little crazy with it. This one's really more like 7/64. And this one over here is more like, that's yellow. This one over here is more like 9/64. Right?
Okay.
Perfectly valid sample space, perfectly valid sample space. Which one's right? There isn't a right one. Which one's more useful?
The top one.
This one or this one?
The top one.
Maybe this one's more accurate. Maybe the yellow here is actually a little bit bigger than the orange.
But that one's more useful to me.
So how would you, if I told you to come up with a way of determining which of these are more useful, how would you do that?
The accuracy.
3D accuracy. So tell me physically what you would do.
Spin it a whole bunch to see
He'd
what
spin
happens.
this a whole bunch of times and see how often it came out each one. And he'd test to see which of these is a better model, right? Which of these is a better sample space? Which of these better model the physical phenomenon? So one of the reasons I love talking about sample space is because it's also a way to give you a notion of what science is, the difference between science and math, and where one comes in and the other ends. Intuitively, what is science? In science, we come across some real-world phenomena, like a spinner.
And you actually spin it.
First thing we do is we construct a mathematical model to model this thing, like a sample space. Here's our mathematical model to model this real-world physical phenomenon. There it is. Second thing we do is we determine the implications or the predictions of our model. This model predicts that orange will come up 7/64 of the time. Third thing we do is we test our prediction. We now start spinning it and we see how often orange comes up. Spin it 1,000,000 times, see what percentage of the time orange came up. And that's how we would determine which of these is the better model. To the extent that a model's predictions are accurate, we call it a good model. To the extent that its predictions are not accurate, we call it a bad model. We eventually get rid of the bad models and we keep the good models. Make sense? Okay. To give you a simple example of that from physics, we assume that we can model forces with a vector. And if you can model forces with a vector, what are some of the implications of that? Well, then you should be able to add forces together the same way you add vectors together. And you can go and you can test that. I think we can still see this. Let me double check. Okay, yeah, you can see that one. All right. So let's move on to another example. This time we'll say that we're rolling a pair of dice. Right? Like in Monopoly, rolling a pair of dice. We want to create a sample space for that. What would my S be here?
1
1 through 12.
1 through 7.
Well,
I can't roll a 1, first of all.
Oh, 2 through 12.
2 through, well, no, because it's 24.
2 through 12. No,
Oh,
it's
2
not.
through 12. Yeah,
Yeah.
you're asking
2 through
me.
12, that's one way you could do it. So
Oh, you could do 1 through 11.
let me show you why that's kind of a hard way to do it. Oops. So you're thinking S would be 2 through 12. 2, 3, 4, 5, ... 12, right? You'll see that part of the reason that's kind of a bad way to do it is then what's our probability? What's the probability of 2?
Small.
1 11.
1/11.
You guys are killing me.
It's not
One.
2 6-sided dice. What are all the possible rules?
You can get 2 1s, you can get 1 and 2, you can get.
So
So it's
ha-
124.
Oh my God.
It's 1/6.
We have 2 dice. How many options are there for what the first die shows?
6.
How many options are there for what the second die shows?
6.
How many possible rules are there?
36.
36.
I was getting there.
I can get a 1 on the first die with a 1, 2, 3, 4, 5, 6 on the second die. There's 6 options. I can get a 2 on the first die with a 1, 2, 3, 4, 5, 6 on the second die. There's 6 more options. Yeah, you guys. We keep asking the same question in different forms, and you keep giving me wrong answers. Very worrying. If I roll 2 6-sided die, how many possible outcomes are there?
36.
36. If I flip a coin, fair coin, 4 times, how many possible outcomes are there?
4. I mean,
16.
16.
Yeah.
2 for the first, 2 for the second, 2 for the third, 2 for the fourth. 2 times 2 times 2 times 2. 16. Right? Okay. Anyways. So how many ways can I roll a 2?
1 out of 36.
You guys don't do a lot of gambling, do you?
Apparently not.
How many ways are there to roll a 3?
2 out of 36.
2 out of 36. Or 1/18, but we'll keep it that. How many ways are there to roll a 4?
4 out of 36.
No.
3.
I thought you did
6 out of
3 out of 36. I heard you. How many ways are there to roll a 5?
36.
4 out of 36.
oh, now I see the problem. So if we just start with 1 to 11, we could do 1 and 136, 2 and 236.
Well, let's make sure that we're still understanding this. How many ways are there to roll a 10? What are the odds of a 10?
9 now, 36.
9.
What's more likely when you roll 2 die? A 7 or a 10?
10.
A 10. Oh, 7, duh.
You never played
Oh, my.
You
Oh,
play
that's
Catan?
right. We're so dumb.
So you've all played Settlers.
Yes.
What's the number that comes up the most when you roll the 2 die?
6.
7. What are the numbers that come up the next most?
8, 6.
6 and 8. You notice that those are the red ones. I should play Settlers with you guys more.
What is 7?
And have you guys gather around the 10s, the 11s, and the 12s. Because following your pattern, what's the odds of a 12 coming up?
12 out of 36.
Now, at that point, when we got a 12, it's 11 out of 36, right? No. How many ways can you roll a 12 with 2 dice?
Once.
1 way. A 6 on the first and a 6 on the second. Right? How many ways can you roll a 10?
Roll 7,
You
6.
can roll a lot of ways.
A lot?
Yeah.
Like
you
how
would
many?
get like
5,
a 1
6,
and a 9.
5.
I'm just
I have 36 for
6 and a 4.
6 and
3
4.
3 out of 36. No, yeah, 3.
Nine is
No,
4.
yeah, 3 out of
10 is
No,
3,
6 out of
36.
36.
336.
3.
No, it's 6.
I'm positive.
Order matters. So you can get 3 and oh wait, you can get 6 and 4.
You can get 6 and 4, 5 and 5, 4 and 6.
Oh, I was doing.
There's all your
3 and
tens.
7.
12 also.
Right. But as you guys can see, you are having a very tough time figuring out your probability function here. Right? So let's try again, and we'll use a different sample space. This time, we'll use what I think is a more natural sample space. Of course, that's my preference. I may call S the sample space 1, 2, 3, 4, 5, 6, crossed with 1, 2, 3, 4, 5, 6. In other words, it's equal to the set of all the possible ordered pairs I can create where the first element comes from this set and the second element comes from this set.
Yeah.
So it's going to have in there
1
1, 1, 1, 2, dot, dot, dot. We'll eventually get 1, 6. And then when we get through all the ones, then we move on to 2, 1, dot, 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 until we get to 6, 6.
That's way more.
Yeah, that is way more. How many things are in there?
36.
That was quick. 36. 6 options for the first element, 6 options for the second element, 6 times 6, 36. All the possible die rolls, right?
Yeah.
So I made S my set of all possible outcomes, all your possible die rolls. Now notice my probability function. What's the probability of any outcome?
136.
136.
Oh.
So it's P of S is 1 over 36 for all little s and big S, where big S is this thing.
Still think
So the probability of 1, 1 is 136. The probability of 2, 1, 136. The probability of 6, 6, 136.
way less useful
Maybe. You'll see once we get to events how we can do what you were trying to do here. So this one's actually more dynamic and more useful. The other one was pigeonholing, but you'll see how later. Now, just because we better go over this since dice come up so much. 1, 2, 3, 4, 5, 6. Nothing to do with the lecture, just I was disturbed by how hard it was for you guys to get these probabilities. So here's all the possible die rolls. Your first die can be 1, 2, 3, 4, 5, 6, and your second die can be 1, 2, 3, 4, 5, 6, right?
Yeah.
We make a quick grid here, really ugly grid, sorry. So this square represents rolling a 1, 1. So a 2. So this square represents rolling a 2. This square represents rolling a
3, 4.
a 2, 1. Or a 1, 2, however you want to think about it. So this is a 3. This is also a 3. This is a 4, 4, 4. You see it? This is a 5, 5, 5, 5. 6, 6, 6, 6, 6, 7, 7, 7, 7, 7, 7, 8, 8, 8.
Whoa. You do 2
8.
circles?
8. Yeah, I used to do it like that, but my handwriting was way too ugly to read it.
2 circles.
These are the things forever.
It does take forever, but I can read it afterwards. I used to have atrocious handwriting, so I had to come up with a bunch of tricks to fix my writing. Anyways, all the way down to 12, right? So here's all the ways that you can roll a 2. There's only 1, 2 3s, 3 4s, 4 5s, 5 6s, 6 7s, and then it counts back down. 5 8s, 4 9s, 3 10s, 2 11s, 1 12. And when you were playing Settlers of Catan, if you go and you look at the number 10, you'll notice it has, on the bottom of it, 3 dots. Yep. Telling you that there's 3 out of 36 ways to get a 10. 3 of the outcomes are a 10. That's what those dots mean.
We should play Catan next week.
Yeah, we should.
Anyways, complete side conversation. Next example, poker hands. You know poker, the game poker? And we're not talking about Texas Hold'em, although you can think about that too, but just poker where you have a hand in poker. How many cards are in a poker hand?
3.
5.
There's
5 cards in a poker hand.
Yeah, we play Texas. Yeah.
Texas Hold'em, you still have 5 cards in a hand. It's just you have 2 in your hand and then you get use 3 off the table.
I've never played real poker, so I don't know what you're talking
Have you done Texas Hold'em?
about. Yeah, that one. It's the same idea.
Texas Hold'em, you hold 2 cards, and then you get to choose 3 cards on the table that you also get to use.
Yeah.
So you still use 5 cards to create your hand.
Yeah.
So your hand is still 5 cards, no matter which version of poker you're playing. So a poker hand is 5 cards.
Okay.
With me? All right, impress me. How many poker hands are there?
There's 13 cards types.
7.
There's 52 cards.
I have
13 types.
52 cards.
Oh,
How many in a
56.
hand?
Oh, does it matter suits?
Do suits matter? Yes, it's a different
It's game
hand.
Poker, yeah, that's true.
All right. I have 52 cards. How many do I get to choose in a hand?
5.
5.
5 out of 52. No. No.
How many
No.
possible poker hands are there? 52 cards. We're going to pick
10.
5 of them to be in our hand.
Yeah, so 52 times 51 times
52 choose 5.
52 choose 5. That's what I meant.
52, choose 5. That's how many possible poker hands there are.
Oh.
How many ways can you choose 5 cards from a bag containing 52 of them?
10.
A lot more than 10.
That's a really big number.
This number is 52 times 51 times 50 times 49 times 48
Oh, 52 factorial.
all over
No.
5 factorial.
52 factorial.
Or over 120, right?
What was the equation again?
That's how many there are, which is a lot.
Factorial.
Yep.
Alright, so a lot of different poker hands. So if we're creating a sample space for a bunch of different poker hands, what is our sample space going to look like? S is going to be the set of all possible poker hands. It's going to be the set of all possible 5-element subsets of a deck. So one hand might look like, I don't know, we might have ace of hearts, king of diamonds, 10 of clubs, 10 of hearts, and 2 of spades. There's one possible hand. And I can't write out all the possible hands because, not infinite, but there's 52 choose 5 hands, which is a massive number, and I can't write them all. Here's one possible hand, right?
Okay.
So that's what S would look like. What's our probability then of getting a particular hand?
1 over 52 choose 5.
1 over 52 choose 5. So if I'm saying what are the odds in poker that you get the hand, all 4 aces with the 10 of clubs, what are the odds that you get that hand?
52, choose
1 over 52 choose 5, which is a very, very, very small number. Since 52 choose 5 is a very, very big number, 1 over it is a very, very, very small number. It's almost 0. You're very unlikely to get 4 aces. If I dealt you just a poker hand, dealt you 5 cards, the odds that you got 4 aces and the 10 of clubs is very, 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 very small. It's not very likely at all. Right? Okay. So the probability of any poker hand is 1 over 52 choose 2 for all poker hands in the set of poker hands. For all little s and big s. This is big S, sorry. Make sense?
Yeah.
Yeah, there's our sample space for poker hands. Alright, tossing a coin 3 times. Alright, question. If I toss a coin 3 times, what's more likely? That I get 2 heads and a tails, that 2 of the flips are heads and 1 of the flips are tails, or that all 3 flips are heads?
2 heads, 1 tails.
Everyone understand why?
Yeah.
Let's list them all out, make sure we understand. We could get heads, heads, heads. We could get heads, heads, tails. We could get heads, tails, heads. We could get heads, tails, tails. We can get tails, heads, heads. We can get tails, heads, tails. We can get tails, tails, heads. And we can get tails, tails, tails. There's all the possible flips. How many of those flips have 2 heads and 1 tails?
3.
That one has it. That one has it. That one has it. How many have 3 heads? Just that one. So the odds of us getting 3 heads is 1/8. The odds of us getting 2 heads and a tails is 3/8.
Or there's 3 times more chance.
Yeah, 3 times more likely. Now, what's the odds? What do I have better odds of getting? Heads, tails, and heads, or heads and heads and heads?
Heads, tails.
This one's more likely, right?
Both the same.
It's way harder to get 3 heads in a row than to get a heads and a tails and a heads.
Wait,
Yeah,
that's
all
not
true.
true. You get it way less.
No,
It's the same.
I'm throwing you off. It's the same.
No.
It's
Yes.
It's automatic.
It is just as hard for you to flip a heads, then flip a heads, then flip a heads, as it is for you to flip a heads, then have to flip a tails, then have to flip a heads. On your second flip, is it easier for you to get a heads or a tails?
Heads because you're on a roll.
50%.
You see?
Yeah.
All right. So there's a difference between these two scenarios. And you get confused on these left and right. And it's hard to keep it clear in your head. There's a difference between getting 2 heads and 1 tails somewhere in your outcome versus just 3 heads in your outcome. And getting exactly heads and tails and heads versus heads and heads and heads.
Is there a way to find those without drawing out all those?
We'll get into calculating events. Yes, and calculating probabilities for events. So we'll get into that. I'm just trying to give you intuition. We're doing a much bigger, deeper dive than what the author actually did. He just gave you examples of sample spaces and went on his merry way. I'm trying to get your intuition set up, get you thinking about these things before next week because it's not obvious, and so I think I'm going to have to say it a couple times and show you a few examples for it to sink in. All right. So I'm doing overkill compared to what the author did. And it's because probabilities are just so unintuitive that the more times you go over it, the better. Okay, so now move on to our next example. Next example, just a very concrete sample space. Nothing special to it. Here's S, 1, 2, 3, 4, and here's our probability function. Question, is that a sample space? Yes or no? Is SP a sample space?
No.
Debbie says no. Anyone disagree with her?
It's not. I agree with her. Oh, it's a 2.
This is a 2.
No, I'm thinking that 1 plus 2.
This is a 2. I don't know.
Oh, it's not. Yeah.
Not a sample space, not a sample space. Nobody thinks it is a sample space. Why is it not a sample space?
Because
Well,
the
you're missing
function.
the 5 and 6.
We're missing the 5 and the 6 here. All right, let's put the 5 and the 6 in here.
Okay, it doesn't add up to 1.
That does.
All right, so now, who thinks it's a sample space?
I do.
You don't see the other problem?
I don't.
There is another
Oh,
You don't see the other problem?
problem. It does add up to 1.
Look at the definition of a sample space.
You have to have something. You have to have.
Don't make me say
Do you
it.
have to make it a percent, or does it fraction?
No, fractions are fine.
No,
It just has to go to a real number.
Zero. You have a probability.
They have to all add up to 1.
Close to
Has to be
4.
greater.
they add up to 1.
It is greater than 0. 4 doesn't. It's 0.
It's a sample space. There's another problem.
Okay, I knew it, and then you just kept saying it.
Yeah.
You say it.
Yeah.
Don't make it say it.
Doesn't matter how many times I say this is going to fall upwards, you better not believe me.
Well, you say it like that.
Don't believe my tone, believe your own brain. Teachers can be wrong. All right, now looking at this, just make sure we understand the probability function. What's P of 1?
0.1.
0.1, perfect. What's P of 2? 0.4. Sorry. What's P of 3? 0.1. What's P of 4? 0. Nothing wrong with that. That's one I thought you guys would get stuck on.
I almost did, but it didn't say anything in the definition.
Good. What's P of 5?
Oh, I see.
0.2. And what's P of 6? 0.2. And now, what we mean by this notation, sorry, I know this is dense, but you just gotta get used to it. It's too useful. The sum for all little s and big S of P of S means the sum of what you get for when we plug in everything in S into P, and we add it all up. So what's everything in S? 1, 2, 3, 4, 5, 6. So we're saying for every little s and big S, in other words, for 1, 2, 3, 4, 5, and 6, plug it into this function and add up what you get.
1.
That's what this notation means. Yes, this comes out to 1, but I want you to understand this notation, this sum right here,
Yeah.
because you're going to see that a lot with probability, and it's so easy to get confused because it's dense notation. So we're summing up all our probabilities for everything in some set.
Isn't there supposed to be a
If I would have, instead of written capital S here, if I would have instead written the set 1, 2,
Define.
then now this would just be P of 1 plus P of 2.
Should.
Make sense?
Yeah.
Dense notation, but it's so useful to use it that because we can't keep writing out massive sums.
So why did you not write a number on top like you usually do? Because S is.
There is no number on top. S is just iterating over everything in here. We're not giving some starting and ending point. So when I did the sum from k equals 1 to 7 of 2k plus 1, then this was equal to what you get when you plug in for 1, for k, then 2, then 3, then 4, then 5, then 6, all the way up to 7.
Yeah.
This would have been the exact same notation as if I got rid of that, put a k here, and I said k is in the set 1, 2, ... 7. For each k in here, add it up.
So you should have done as equals 1 to 2. Whatever, never mind.
Could have, but you don't typically see it that way for probabilities, because your sample space, your outcomes, your set of outcomes is rarely a number. Okay, so just want to give you examples with that notation. All right, if they're same, 2 problems I want to go over. We'll go over this one because Hayden asked me to a bit ago. I told you guys I would.
Yeah, that would be fun.
All right, here's the problem. If 10% of the population, the US population we'll assume, if 10% of the US population has COVID, and I create a test that's accurate 90% of the time, so my test is accurate 90% of the time, let's make sure you understand what that means. That means if 100 people had COVID and took my test, then 90 of them, it would have said, yes, you have COVID, and 10 of them, it would have said you don't have COVID, even though they all had COVID. My test is right 10% of the time, or 90% of the time, and it's wrong 10% of the time.
Yeah.
If they all have COVID.
My test is right exactly 90% of the time, and it's wrong exactly 10% of the time. You with me?
Yeah.
That's what it means for the test to be accurate 90% of the time. Okay, so now, my test is accurate 90% of the time. What are the odds that you have COVID, given that you have a positive test? So 10% of people have COVID-19. I develop a test that's accurate 90% of the time. You're wondering, do I have COVID? You go, you take a test, it comes back positive. What are the odds that you actually have COVID?
10%. No.
What? That was the odds you had COVID even before you took a test result. The fact that you got a positive test result doesn't change the odds that you have COVID.
10% times 10%.
1/90th.
1/90th?
Is it?
1/90th is almost 1%.
Well, you do. 10%.
That you do have COVID after taking a positive test result. There's only a 1 in 90 chance that you actually have COVID after you take a test that's 90% positive.
Oh.
I mean,
1/9.
yeah.
Isn't it 5%?
I don't know where you come up with these numbers. It has to be more than 10%.
It's 100%.
10% are the odds that you have COVID before you even took a test. All right? If 10% of the US population has COVID, the odds that you have COVID without any test are 10%. Okay, now you got a test that says you have COVID. It's a positive test result. The test is right 90% of the time. What are the odds that you have COVID?
So you have 1 to 10.
Well, don't we have to start with 300 million? Because that's how much
It would be less than 10.
No, because we're talking about percentages.
You're saying it gave you a positive on the test.
The test came back positive. It says you have COVID.
Why would it ever be more than 10? 80%.
Why would it ever be more than?
If you have 10% to start, and then sometimes you're wrong, the test, and it says you don't have COVID, that would be less chances that the test says
But
you do.
90% it says you do have COVID.
You
Yeah,
have
so
a
that's
test
what I'm
that's
saying.
right 90% of the time. You go to the clinic. The clinic gives you a COVID test. They say our tests are 90% accurate. The test comes back positive.
You just believe.
What are the odds that you have COVID?
Okay, so
It's
you're
like
1 out of
80%.
100, and your test is 90% accurate. So it's 90% of 1/10,
1 time times 190.
right?
No.
So 90% of 1/10 is 9%.
9%.
A test that's 90% accurate.
0.9 times 0.1 is 0.09.
It won't change it. It should be 110. Should be 10%.
Is it not?
Should be 10%. It doesn't matter that you have a positive COVID test result. Why would you go take the test if it doesn't change the odds that you have the thing?
I'm trying.
What if you took 1,000 tests in a row and they all came back positive? What are the odds that you have COVID?
Of really, really high.
Really, really high. So you know that taking a test changes the possibility that you have COVID. So it for sure changes it.
So there's 90% chance.
There's a 90% chance that you have COVID
If you had the COVID to start.
if you had the COVID to start. You don't know
Yeah.
whether or not you have COVID.
So 90 times 10. 10% times
10 times 10% times 90?
Oh, put one,
One tenth times 9/10.
9%. So it's less?
I want 9% every single.
Oh wait, hang on. Is it?
Is it 50%?
The answer is 50%.
Let's go.
Wait. How did you know?
All right,
No, hang on. How did you know that?
let's go over it.
Think of it like draw it out within your brain. Yeah, he's gonna do a diagram and you'll see what I was thinking.
Here's the population. We'll pretend that the US population is just 100 people. Doesn't matter, since we're going to be talking about percentages. We're just going to assume 100 to keep the numbers nice and even. You with me? Now over here, we have your people that have COVID. So there's 10 people over here and there's 90 people over here.
Okay.
Don't have COVID, do have COVID. Now we give every single person my test. With me? Of these 90 people that take my test, that all have COVID, how many of them is my test going to say, yes, you have COVID? 90% of them. My test is right 90% of the time. It's wrong 10% of the time. If 90 people go and take my test who all have COVID,
Don't.
oh, sorry.
Yeah.
Oh, I meant to do the one that does have COVID. Sorry. Let's do the one that does have COVID first. Sorry. Because I was trying to do the simple math first. 10 people have COVID. They all go take my test. My test is right 90% of the time. How many of them is it going to say, yes, you have COVID to? 9 of them, or 90%. How many of them is it going to say, you don't have COVID to? 1. Okay, now all these people go and take my COVID test. How many of them is it going to say, you don't have COVID to? 90%, right?
Yeah, because it's accurate 90%.
What's 90% of 90?
81.
81. 0.9 times 9 is 81. Carry the decimal place. All right. So, it's going to 81 people are here. It's going to say you don't have COVID. 9 here, it's going to say you do have COVID. So this was the ones who my test said positive for, and these are the ones my test said positive for. It said negative to these people, negative to these people.
18%.
So, if 100 people take my test, odds are 18 of them are going to get a positive test result.
That's close enough to 50. No.
No. Of those 18, how many of them actually have COVID?
Half of them.
9.
Oh my
So
god.
9 out of 18,
Oh,
which is 50%. So if this were the case and you went and you got the COVID test and the test was only accurate 90% of the time, and you went and got the COVID test and it came back positive, there would have only been a 50% chance that you actually had COVID.
So the question was, if
That's
the
so
test told you you had COVID, what's the chance that you
I'm
had
never
COVID?
taking that.
Well, that was based on these numbers. I'm not saying that that was actually the case.
I know,
But now here's something very dangerous that people do all the time. If I were to ask you how many people had COVID, what would you go Google?
What percent of the
You
US
go
is-
Google how many people have COVID, and we come back and say, this many people have tested positive for COVID. And you say, oh, that's how many positive test results there were for COVID. So that's how many people had COVID. No, I'm not saying that's how you right now would. I'm saying your typical person, if they were just to think of a question, a random question, how many people have had COVID?
'Cause we
And they
don't-
were to go Google it, what would they see?
We don't know how many people actually have COVID because the
They
test
see how
is
many positive
right
test
50%.
results. And so in our scenario, if only 9 people did it, but you did a Google search, it will come back with 18 people had COVID when really only 9 had COVID in this scenario.
10 have COVID.
It's another danger to understanding probabilities and statistics, in particularly here to understanding a statistic. Oftentimes you go and you Google statistics to things, and your brain, you just naturally interpret it thinking you know what it's saying. Google comes back and says there's been this many positive cases of COVID. You naturally, or most people are going to assume, oh, that's how many people have had COVID.
So
Right?
does that mean that there wasn't actually that many people that had COVID?
You cannot just look at, what it means is that you cannot just look at the positive results and conclude how many people have actually had COVID. And answering the question, how many people have had COVID, is not a trivial question. That's a hard question to answer.
Right.
You can't unless you have 100%.
So even with basic statistics that people are using left and right all the time, how many arguments were there about COVID? Left and right. And how many people even understood this basic fact about test results? I think it's something of 80% of PhDs, or not PhDs, MDs, will get this question wrong. So they don't understand those results. And there's a reason that they don't understand it. It's because it's not intuitive. And they're not trained to understand this. They're trained to help an individual person deal with their individual illness. They're not trained to, based off of statistics, come to probabilistic conclusions. That's what actuaries are trained to do. And it's not easy to become an actuary.
Actuaries are in statistics, probabilities.
That's what an actuary does. They calculate probabilities based on statistics,
Nice.
particularly for risk analysis. And it is a pain. There's a reason that they make a ton of money to do it. All right, let's try one more question with the remaining time. Gonna play a game with you. You have a 6-sided die. Okay? Every time you roll a 3, I give you $1. Every time you don't roll a 3, you give me $1. Is that game fair?
No.
No, not even close. To make the game fair, I have to let you try to roll a 3 how many times?
3.
I have to give you 3 chances to try and roll a 3, right?
And it's
No.
No, 2.
2.
Yes.
3 makes sense.
2, 3, what do you think?
2.
How can we make this a fair game?
Oh.
3 makes intuitive sense.
How many chances should I give you to roll the die to make it a fair game?
Once.
Or can we not make it a fair game?
Once.
Well, I
6.
guess. Yeah.
One chance?
6.
Okay, I will play this game with you.
Because if you roll it once, then it's 50-50. That's fair.
No, it's
So
not.
you have a 6-sided die.
Oh,
You roll a 3. If you get a 3, I'll give you $1. If you don't get a 3, you give me $1. We can play as long as you want.
That is not fair.
Yeah, it's not fair.
But if you're
Okay, what if I give you 3 chances to try and roll a 3? Then is it fair?
No. It's not.
Intuitively.
It's not fair?
It's never going to be fair.
It's never going to be fair?
No, because
Well,
I have
guess,
1/6 of a
yeah, but
chance.
you have to do.
What's the odds of you rolling a 6 or rolling a 3 on your first try?
1/6.
1 in 6. If I gave you 3 chances to try and roll a 3, what are the odds you're successful?
1/3. 1/2.
1/2, right?
Because you keep the
Oh. Well,
It-
yeah, I guess.
Yeah. So if I give you 3 chances to try and roll a 3, then you'll be able to do it 50% of the time. And that makes the game fair, right?
No, because then there's
Because
3
then there's
rules.
still a chance where you get 75%.
I'm not sure where that number's coming from.
Well, not like 75%, but more than 50.
If I give you 3 chances to try and roll a 3, what are the odds that you do it? I give you 3 chances.
50%.
50%. So here's the game. I give you 3 chances to try and roll a 3. If you roll a 3 in one of those 3 tries, I give you $1. If you don't roll a 3 in all 3 of those tries, then you give me $1.
Oh, like that.
Yeah,
okay.
so it's fair.
Okay.
Is that a fair game?
That's more fair.
Yeah.
Yes.
The answer is no.
No,
It's
yeah.
not a fair game. I'm ripping you off.
Because your intuition
Yes.
likes it.
Because you have.
But
You play this,
50% of-
you teach this class, you start to think you should open a little local casino.
That's true. You
You
can write it
would
off
be
so
fair.
hard.
All right, so let's go over why 1/2 is wrong. So in 3 tries of rolling a 6, then you were saying that, or if I have 3 chances to try and roll a 3, then that will happen 1/6 plus 1/6 plus 1/6 at a time, right? What if you give me 10 chances to roll a 3? What are the odds I get a 3?
That's not
100%.
Oh, what?
And
No.
you give me 10 rolls of the die. What are the odds I get a 3?
It can't be 100%.
It's not 100%,
It's
right?
not, it's like 190.
No,
And it can't be 100. It has to be less than 100%.
Yeah, it has to be.
So your simple way of thinking about this is wrong.
Hang on.
It doesn't work.
10/6.
So how can we solve this problem?
That's 40%.
10/6 is more than 1.
10/6 is 40% of the time.
Yeah.
So 40%,
You know what I mean?
0.4.
1 2/3.
which is the same as 2/5. Huh. That's a stretch.
If you divide 6 by 5, you get 5.
However you come up with that, okay.
I went like this. You add up to 1, and then you get 4 more, and delete that one.
We just delete the 1. Okay, so if I give you 7 tries to roll a 6, what are the odds you're successful? 1/6,
1/7.
1/7/6.
1/7. So the odds of getting a 3 in 7 tries is less than the odds of getting a 3 in 1 try. So you better stick to just 1 try.
Yep.
Now that doesn't work.
2 7s.
Now you're just spitballing.
Yeah, you're right. Oh, wait, hang on.
All right.
3 18s, 6
So here's a way to think about it. How is it possible for you to lose the game?
If you don't roll 3 on all.
If you don't roll a 3 times in a row? What are the odds of not rolling a 3 once?
1 2 5 6.
5/6. What are the odds that you don't roll a 3? 5/6. What are the odds that you don't roll a 3 twice in a row?
5 6 times
5/6 times 5/6. What are the odds that you don't roll a 3 times in a row?
5 6 times.
5/6 times, oops. 5/6 times 5/6 times 5/6, or 125 over 216. Right?
Yeah.
So this is the odds that you don't roll a 3. So what are the odds that you do roll a 3?
1/6 times 1/6 times 1/6.
No.
Oh.
Look, if I told you that there was a 40% chance of you rolling a 3,
1 minus that.
what are the odds that you don't roll a 3?
1 minus
60%, or 1 minus it. So if these are the odds that you don't roll a 3, what are the odds that you do roll a 3?
91.
91 over 216.
Yeah.
Together, they have to add up to 1. 125 over 216 plus 91 over 216 is equal to 216 over 216, or equal to 1. So this is the odds of not rolling a 3 in 3 tries. This is the odds of rolling a 3 at least once in 3 tries.
91 to prime.
So you're far more likely to not roll the 3 than you are to roll the 3.
So would you be more likely to roll the 3 times?
Because what is this going to come out to? Roughly like between 45 and 40, like 42, 43%.
So if you did it out of 6,
So this is going to be somewhere like 43%. I don't really know exactly what it is.
we stop.
And so this one up here is going to be roughly 57%. And so if we played the game, on average, every time the game is played, assuming I'm this person here, I can expect to make 14 cents from you every time the game's played. In other words, if I can get you to play the game 1,000 times, I would have made 140 bucks off of you. If I could get 1,000 people to come to my casino and play this game, at least once, or exactly one time, I would have made 140 bucks.
If you did choose a 6, 3 out of 6,
But scam like, so it's obviously not gonna be like $1, it's gonna be
People play roulette. It's a scam.
like, true.
So, I don't know. And roulette, it's obvious it's a scam. This one, you can kind of hide it behind people's intuition.
Yeah.
So you come up with some clever games to trick people into giving you their money. If you're so inclined. I'm not saying that's a reason to stay this stuff, but hey, if it helps, it helps.
Makes me wonder,
Just want to match it probably.
do the Vegas casinos just hire mathematicians?
No, the math in pretty much all their games is pretty straightforward.
So they're just dummies.
It doesn't take a lot of math to figure out the odds for most things. Like roulette, I don't know how many sections there are in roulette.
9, something like that.
No, it's like 40.
Yeah.
But then one of them is marked with the green. So there's a green space, so there's a little bit less than 50% chance of it being red, a little bit less than 50% chance of it being black. But when you play roulette, you only double your money if you guess red or black right.
why is that unfair? Because of green.
Because there's a green one. So in roulette, it's split so that you have, it's split into a bunch of things.
That's fair. That's
So
not fair.
almost half of them are red and almost half of them are black, but then there's a green one, or 2 green ones, I don't remember. 1 or 2 green ones. So there might be 2 green ones.
So there's a higher probability.
Either way, so less than half of them are red. But when you bet your money on red, you only double your money if you're right.
Are you betting against the house roulette or against people?
you're going against the house. You're just guessing what it's going to land on.
So yeah, the house does win.
Yeah, that's how most
So you
games
don't
are set
think
up.
they hire mathematicians at all?
Well, they might hire mathematicians for things. It's just, I don't know the game that you really need a
Mathematician for.
actuary type mathematician for. Even when you're like
either way, they're gonna be
doing your basic calculator, driving your calculator for what's it called? 21. You could do the math pretty much with everything we talked about in this class.
Advantage of your psychology.
Huh?
Don't they take more advantage, like they take advantage of your psychology more than like your human instinct more than?
Well, so there's an event, a psychological event that happens a lot of time with people in where they think they get lucky. The best example I can think of is, so every girl who gets pregnant pretty much tries to guess the gender of her baby. That happens almost universally.
Okay.
So now imagine that we got 8 pregnant girls, and 8 girls, and each of them has had 3 kids. Just playing the odds, one of those 8 girls guessed all 3 genders of her kids right. One of those girls guessed all 3 genders of her kids wrong. And then you got 3 of them that guessed 2 right and 1 wrong, so they think they're doing pretty good. And you got another 2 who guessed 2 wrong and only 1 right. Now, when you guess the gender of your baby wrong, you're not very vocal about it. But then if you go 3 for 3, that's pretty good. You're probably going to be a little bit vocal about that. So 1 in 8 girls out there are running around convinced that they have some strategy for predicting the gender of their baby.
That's always boy.
You have a similar thing happens with like roulette. People go, they don't realize you're one of a bunch of people. It's possible to just get lucky. You think it's because of the system you came into the game with. Turns out you were just lucky, and if you keep trying it long enough, you're going to lose. So that's how psychology often comes in. Anyways, bit of a weird tangent.
See you later.